Hello, today we're going to talk about point forces. So starting out with the definition, a point force is any force with a single point of application. So in statics we're going to be dealing with a lot of point forces. So these forces can be represented as a single vector, and each point force has three important characteristics, just like any force. So for example, we've got this body over here, and we've got this vector acting on it. It's going to have a magnitude. That is the 100 Newton magnitude we have there. It's going to have a direction. In this case, it's kind of pointing up, which we usually call the positive y direction. And it's going to have a single point of application. So this is where point forces differ from distributed forces. Distributed forces are kind of spread over an area. So with our single point of application, we're kind of acting on the left edge of this beam over here. So with almost every force, it's actually applied across some area or volume, but we approximate many forces as point forces. So first thing would be something like tension in cables. The cable actually has some thickness or some diameter to it, so it's not a single point that we're applying this tension force to, but really they're so thin that we usually just approximate tension forces as point forces. Something like this friction force, we've got a bow being drawn across a cello here. So with this, there's a small area of contact there, but really we'd approximate this as a point force. Another one that is usually not a point force in reality, but we approximate it as a point force, is gravitational forces. So this volleyball has some weight. Gravity is going to be pulling down on every little bit. It's actually known as what's called a body force. But in many cases, we approximate the gravitational force as a single force acting on the center of mass of our body. And finally, we've got this table over here. Here we've got a couple what we would think of as point forces. We've got gravitational force, which we're going to model as a single force acting on the center of mass of the body. And on each of the two legs here, we've got a normal force pushing up. So in many cases, we've got these point forces, and we treat them, we've got these forces, and we treat them all as point forces. So these point forces are vectors, and they're going to have a magnitude and direction, and the vectors are represented by bold characters. So whenever you see F in bold, it indicates a force that has both the magnitude and direction. So you need to be careful when you're working with these in your equations, because you can't just treat it like a number. So to show the different magnitude and direction, we can use two different methods that are commonly used in statics. So the first is to use the overall magnitude. So I'd say 100 Newton force. To show the direction, I'd use an angle. But we can also say the magnitude in each of these components. So I've got a force. It's so much pushing so much in the horizontal direction, so much in the vertical direction. So to kind of illustrate this in 2 dimensions, we're going to have the same force in 2 different ways. So we could do a magnitude and an angle. We've got a 30 Newton force acting 30 degrees above the x-axis. But the same vector in component form, we're going to have about 25.98 newtons in the horizontal direction and 15 newtons in the vertical direction, or the y direction. So this is the same vector. This is going to be magnitude and angle. This is component form over here. So in 3D, we're going to have 2 different angles for the magnitude and direction. So I've got a 30 Newton force, and it's going to be 30 degrees out and about 45 degrees up. So we need those 2 angles to fully define our direction in 3D space. Or in component form, we have an x, a y, and a z component. So you'll notice that the numbers of kind of independent things we need to deal with depends on our number of dimensions. So in 2 dimensions, I had 1 angle and 1 magnitude, or 2 components. In 3 dimensions, I had 2 angles and 1 magnitude, that's 3 unknowns. Or 3 components, which is 3 unknowns. So either way, same number of unknowns, or same number of kind of variables to describe fully this vector. And one of the big things we're going to have to do is convert back and forth between these different forms. So to go back and forth, we're going to use trigonometry. So we've got something like this, and we think about using these right triangles. So the components are always going to be perpendicular to one another. That's what the components do. So in x and y, if we have magnitude and angle, we're going to have the hypotenuse is going to have a length equal to the overall magnitude. And we've got some angle theta. It could be over here, it could be over here, it could be somewhere in that right triangle. You have to be careful about where you put that so it matches your diagram. So we draw this triangle out, and we're going to use the following three identities. So sine theta, the sine of this angle here, is going to be equal to the opposite over the hypotenuse. Or cosine theta is adjacent over hypotenuse, and tan theta is opposite over adjacent. So in this case, the x component, the horizontal component, is adjacent. The y component is going to be the opposite side. And hypotenuse is the overall magnitude, and I've got some angle theta. So say I wanted to go from magnitude and angle, so I'm going to know the hypotenuse and this theta angle here, and I want to go to component form. I'd say, well, I need to figure out the opposite, and I need to figure out the adjacent. So to find the opposite, I know theta, I know hypotenuse, so I can use this formula here to solve for the opposite. So to find the opposite side, I'd take sine theta, I'd multiply it by the hypotenuse, and that would give me my y component, the opposite side. For the adjacent side, that's going to be my x component. I'm going to need the adjacent. I know hypotenuse, I know cosine, or I know theta. So cosine theta times the hypotenuse would give me the adjacent side, or the horizontal component. So that is going from magnitude and angle to the other one. If I know opposite and adjacent, I can figure out my angle theta. That's my that's going to be my angle here. So I can figure out the direction, and actually to figure out the overall magnitude, I can use the Pythagorean theorem. So adjacent squared plus opposite squared is going to be equal to, or adjacent squared plus opposite squared is going to be equal to the hypotenuse squared. So you do need to be careful, though, depending on how you set up your angle. So if I measure the angle from vertical, what used to be, the opposite used to be the y component. Actually now, the opposite side from the angle is my x component. So by changing how I've defined this angle, I've changed what counts as the x component and what counts as the y component. So at least beginning off with some of these things, my recommendation to you is always draw out these triangles, think about what's the x component, what's the y component, and the hypotenuse is almost always going to be your overall magnitude. And just use these identities to solve out your individual parts. So with that, next we've got converting between forms in 3 dimensions. So in 3 dimensions, we're going to need to use a set of 2 triangles to convert back and forth. So this is magnitude and angle form. I've got 2 angles, 30 degrees, kind of out like this, and then 45 degrees up. And I've got an overall magnitude of 30 newtons. Here I've got x, y, and z. So using that 45 degree angle first, I'm going to use this triangle. So it's a triangle, it's underneath the vector, and it just goes straight down to the xz plane. And in this triangle, that's my right angle right here. So if I know this angle, it's going to be 45 degrees. This is a 90 degree angle, this is a 45 degree angle. The opposite is going to be my y component. That's the opposite part of my triangle here. Adjacent is going to be kind of this length from here to here. And the overall magnitude is going to be that 30 newtons. That's something I know. The second triangle, once I figure out the y component and this length here, I can use this other triangle. And so this is a triangle laying in the xz plane. And my right angle actually doesn't look like it, but it'd be sitting over here. And I know that this angle right here is going to be 30 degrees. So by using these 2 triangles and an intermediate step. So I had to figure out along the middle, I had to figure out this fxz that is an intermediate step along the way. I can figure out my components in the x, y, and z direction if I know my initial magnitude and these two angles. And you can kind of do the same thing in reverse to go from components back into the magnitude and angle form. So with that, that's all I have for this video. Thank you for watching, and I hope to see you again.